Hello, I would like to do a quick sound check before we start. If you can hear me, please type yes in the questions tab. Okay, great. I'm seeing some responses come in. Thank you. Hello and welcome everyone. Thank you for joining us today for our webinar titled Fairness in AI and Machine Learning. My name is Patrick Moran and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Navdeep Gill is a senior data scientist, software engineer at H2O.ai, where he focuses mainly on machine learning interpretability and previously focused on GPU-accelerated machine learning, automated machine learning, and the core H2O3 platform. Prior to joining H2O.ai, Navdeep worked at Cisco, focusing on data science and software development. Before that, Navdeep was a researcher/analyst in several neuroscience labs at the following institutions: CSU East Bay, UC San Francisco, and the Smith Kettlewell Eye Research Institute. Now, before I hand it over to Navdeep, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. Now, without further ado, I'd like to hand it over to Navdeep.
Thanks, Patrick. So the title of the talk today is Discrimination in Machine Learning. So today I hope to just kind of go over what to avoid when it comes to machine learning and discrimination in your machine learning application. I would also like to go over some type of workflow that you can follow. Today you will not receive some type of silver bullet to avoid this type of thing. Avoiding any type of bias or unfair treatment of certain groups in machine learning takes a lot of effort on the data scientist or analyst part. But I hope that you will find some tools that you can use from here, some examples, and some metrics you can look out for in your applications. Before I go to the next slide, I should let you know that a lot of the information I'm giving today, it should not be considered legal advice. It's just stuff that I have learned and my colleagues have learned through the literature and through our own experiences. So just to go over the contents we'll be covering today, we'll kind of go over why you should care about discrimination in machine learning, what it actually entails, and how it can come about and what you can do to prevent this type of thing from happening. So here are a few bullet points about why you should care about discrimination in ML. So the first thing is reputational risk. So there is an article called Why Addressing Ethical Questions in AI Will Benefit Organizations, and the article mentions that 34% of consumers are likely to stop interacting with the company once they've perceived any unethical actions by that company themselves. So if anything else, this should be very important to a lot of business and stakeholders. I think a lot of times once a consumer encounter some unethical behavior, whether it be intentional by the company's part or unintentional, they will not be able to decipher the difference. At the end of the day, they saw some unethical behavior and they're more likely than not going to trust that product or software anymore. And once that trust is lost, it will be very difficult to obtain back again. So that's the first bullet point I like to mention on why you should care about this, this matter. The next bullet point is responsible practice of machine learning. So in any machine learning application, you should strive to have some clear understanding and trust of your ML system's behavior. I think this is something a lot of analysts, engineers, people in healthcare, researchers, scientists, and humans in general, they have a need to understand and trust a lot of things that they encounter. And so in this case, you should apply the same to machine learning models themselves. So having this clear understanding and trust of ML systems behavior should be something you should strive for, whether you're in a regulated industry or an unregulated industry. This is something that's very important, and this is sort of the clear, responsible practice of ML. Now, another aspect of responsible ML is, you have to have rigorous vetting of an ML system, especially when it comes to high-stake applications. And by high-stake applications, I mean applications that affect people. So some examples of these are fair lending, credit scoring, facial recognition, healthcare diagnosis, recidivism. These are very clear examples of where ML can be applied, and these are very clear examples where irresponsible ML can cause devastating results. If you're not practicing responsible machine learning for fair lending, you might deny a person a loan for a house, even though they're well-deserving. And in this case, obtaining a house is a big change in a person's life, a big change in a family's life, and you want to make sure that the tools you're using are being used in a responsible manner. Credit scoring follows the same way. The more credit we allow people, the more opportunities they can gain in their life. And once again, if we're not doing this in a responsible manner, we're denying people ways to improve their life. Facial recognition is also important. So if the application of facial recognition is some type of surveillancing or anything like that, and the recognition is not doing a good job, or it's not doing a responsible job, you can also, once again, cause some serious damage to the population. And of course, the same applies to if you're trying to predict repeat offenders out of the prison system. You want to make sure you're doing an accurate job of that, because if you're not doing an accurate job of that, you might deter them into progressing in their life and improving oneself. The last bullet point is more of a so applies to regulated industries, and if in those industries, if any type of discrimination is found in a machine learning model, then you might end up with fines. You might have some litigation brought upon you, and these all have costs. So that's sort of the last point I want to bring up about the why when it comes to discrimination in ML. So this is sort of a pictorial of what elements you might see in responsible ML. You sort of have this one circle that has to do with trust, and another one that has to do with understanding. So with the trust, you have to be able to benchmark your models, make sure that the feature engineering is fair, secure, and private. You should be able to get rid of old models or stale models that are not performing to the level you want based off of the samples coming in. You want to assess the models, make sure that they're accurate, and they're also giving results that make sense. You should be able to debug the models, test for bias, have the ability to appeal a decision of a model to sort of debug and see what the model's thinking. The model should be reproducible. So these are the type of things a data scientist or an analyst or a stakeholder should look for in their machine learning model. And on the other circle, you have understanding. So this is typical things like exploratory data analysis, straightforward feature engineering, sort of manual feature engineering, causal or constrained interpretable models, the ability to do post hoc explanation, and human review and documentation of the model, which is seen a lot in many domains, particularly banking or insurance, where they do a rigorous documentation process to ensure all their steps are covered. And if you sort of look at the intersection of these two, maybe you can come up with some type of causality. I'm not saying 100% causality, but maybe you can, by combining trust and understanding, you gain a better machine learning model itself, and combining those two, you're able to move forward with your application in a more responsible manner. So the next step is I'll sort of go over what bias is from a machine learning standpoint. So almost all data, statistical models, ML models, they have some type of bias in them. And this is sort of a misrepresentation of reality. So when it comes to data, the data used for the model itself is a sample. So hence it's not actually reality, it's estimation of reality, since we cannot collect all data that is available to us. So in that regard, we do have a misrepresentation of reality. We have an estimation of reality. And based off of that, models will have their own sense of reality of what they think is going on based on the data that is given them. So that in itself is sort of a bias that we're introducing. This is just the nature of machine learning. Like I said, we can't collect all data that is available. We take on samples, and we ensure that the sample is as representative as possible. So bias can also be helpful. So think of a penalized linear regression, bias variance trade-off. This is when bias can be helpful because you're minimizing variance in sort of your coefficients for a linear model. But bias can also be unhelpful, unwanted, and it could cause some illegal discrimination. An example of this is penalizing observations based off of race, gender, socioeconomic status. These types of things are a type of unhelpful bias that we would like to avoid. So next step is what is discrimination in ML? So ideally, we would want model predictions to be independent of demographic group membership. So once again, this goes back to high-stake ML applications. So before I mentioned things like fair lending, credit scoring, facial recognition, healthcare diagnosis. These types of applications of machine learning are very high stakes. And once again, high stakes is when you affect people's lives, you affect sort of the next step they might encounter in their life. And in this case, we want to make sure that whatever the model is producing is independent of those demographic group variables. Now, in these applications, the model exhibits discrimination if a demographic group membership is not independent of the likelihood of receiving a favorable or accurate model prediction. So this is sort of an example of this is sort of if females are treated differently than males in, let's say, a fair lending application. The second bullet point of when you can see discrimination in the model is if membership in a subset of a demographic group is not independent of the likelihood of receiving a favorable or accurate model prediction. So this is called local bias. So the first one I mentioned was demographic group membership. So this is typically male versus female and used in a fair lending application, and you see some discrimination happening based off gender. The second bullet point, where your membership in a subset of the demographic group, this is local bias. So this is, let's say, male versus female in a fair lending application shows no discrimination based off of your post hoc analysis. But once you start zooming in to certain females versus certain males, you start seeing some bias arise. This is called local bias, and we'll talk about this more later. So there are several forms of discrimination that you might see in machine learning. There is the first one is intentional discrimination, and this is known as disparate treatment. So this is just blatantly using a variable such as gender or race to predict whether a person should get a loan or not. Nowadays, you don't really see this anymore. Banks are obviously trying to avoid this. Insurance companies are trying to avoid this, and they're testing for this. So this is something that is pretty much covered in today's practice. The one that can creep up on a data scientist or an analyst or some stakeholders is unintentional discrimination, which is called disparate impact. So this is the case when you use a variable that you think is a reasonable predictor of an outcome, but it introduces some demographic group bias. So think of a variable that might be highly correlated to a demographic group variable. An example of this might be, let's say, typical credit score, which has been shown to be different for certain ethnic groups versus other ethnic groups. So once again, this might be correlated to a demographic group variable, and you might think to yourself, it's fine to use in your model. You do some post hoc explanations, and you find out there is some disparate impact that has been introduced by using this model. So like I mentioned here, most models can be checked for this post hoc by using this concept known as disparate impact analysis. And I'll sort of go over this later as well via notebook and also through driverless AI. Now, discrimination in ML may or may not be illegal. It all depends on how it arises, and it depends upon the discrimination laws that could have been broken. So regulated industries might investigate potential discrimination in ML applications more so than unregulated industries. But however, that's not always the case. Sometimes it could be very clear that some discrimination is happening. Other times it might be a gray area. So in one case, it might be blatantly clear that some discrimination is happening. In another case, it might be stuck in a gray area in which some debate needs to happen. So we'll continue on with what is discrimination in ML. So it can originate from the training data itself. So think of just having incomplete or inaccurate data that is not a good representation of all minorities in your potential population that you're trying to target with your ML application. You can also have accurate but differing patterns of causation, correlation, or dependency between demographic groups and past outcomes. So like for example, a traditional FICO score, which can be different for certain demographic groups, and that can cause some disparity in your ML application. And you can also introduce some type of discrimination through your training data if you have explicit encoding of historical social biases. Think of things like criminal records or times a person's been bankrupt. These are sort of social biases that can arise in data itself, and it can cause some underlying disparate impact in a machine learning model. So the ML model itself can perpetuate or exacerbate discrimination. So this will cause, which might cause seeing things like group disparities, so different or inaccurate treatment of entire demographic groups. So, the model might learn different correlations between demographic groups and favorable model outcomes. And this is considered adverse impact, and we'll go over that in a later slide. And the model might also exhibit differing accuracies across demographic groups. This is known as differential validity. So different accuracies meaning maybe the accuracy metric is significantly different between males and females, or is extremely different between minority groups versus Caucasians, for example. Now, another thing you might see is, like I mentioned before, local bias, and this is different or inaccurate treatment of similar individuals. So maybe the local response function or the decision boundary for the model itself shows some disparate impact at a local level, but not at a group disparity level. This thing is pretty hard to identify from doing something like disparate impact analysis. It does involve a lot more data mining in your post-hoc explanation process. So there are many kinds of group disparities that can be measured. So you can look at a lot of different metrics across groups. Something like true positive rate, true negative rate. You can look at certain machine learning metrics like how accurate the model is, things of that nature. So in this case, I'm going to just go over a few. So you can look at accuracy disparity. So you can compare the accuracy of your model for your protected group. So this is accuracy P. So let's say the protected group is female, and you can compare that to the accuracy group of the reference level, which in this case would be male. So this would be a ratio that you can look at, and then you can see if it goes over some threshold that you're interested in. You can also do the same with adverse impact ratio. So this is the percent, let's say that received a favorable outcome for your protected group divided by the percent that received a favorable outcome for your reference group. So in this case, think of the protected group as females and the reference group as males. So that's adverse impact ratio. And you can also look at the next one, which is marginal effect, which is you take the difference of the two. So the difference of the protected group minus the difference of the reference group. And you can also, in addition to that, look at the standardized mean difference. So this is if you took the average response of the protected group minus the average response of the reference group and divided it by the sigma of your response. So these four metrics are pretty common in regulated industry, fair lending, and this is something you can apply to your machine learning application today, and you can also use it today in driverless AI, which I hope to show later on. So like the last bullet point there, like I mentioned before, local bias is much trickier to measure, and it can often lead to some unmitigated risk for consumer-facing ML applications. So if we were to look at these metrics at a group level, let's just say comparing males to females, different minority groups, different education levels, you might find that there is no bias happening or no discrimination happening. But sometimes if you dig a little deeper into the local aspect of it, maybe you cut and slice the data a little bit more, you might uncover some discrimination happening in your machine learning model. So the reason local bias is trickier is it involves, let's just say, it involves more steps in your process to sort of uncover these type of things. So we've gone over, why you should care about discrimination in machine learning, what it is in its various forms. The next step is, how can you fix it itself? So the first step is you can fix the process. So the process meaning, the experience in design, training, and review of ML systems. So building an ML system is an entire process, and you can incorporate a responsible ML approach from the beginning to avoid these type of issues. You can also fix, so in addition to that, you would start off by fixing the data. You would make sure that your training data is very representative of the population you're targeting in terms of demographic groups, gender, certain education level, anything that your model might uncover as some bias. You might want to use features that are more judicious in a sense. So instead of using time on file for, let's say, a banking application, you might, instead of using a bankruptcy flag for a banking application, you might use time on file as a feature. And you can also sample and reweigh training data to minimize discrimination. So there are certain ways if you cannot collect all the demographic information you want, you can use some sampler reweighting to sort of fix that and remedy that problem. You can also fix the model itself. You can try to consider fairness metrics when selecting hyperparameters and cutoff thresholds. You can train fair models. So one example is LFR, learning fair representations, and adversarial debiasing, which I have references to here. Another thing you could do with a fair model is use a dual objective function. So, you can use accuracy as an objective function along with some fairness metrics that you're willing to go after. And the other thing with modeling is you can train various models and try to obtain the model that is pretty accurate but also keeps fairness in mind. So this involves a lot of model comparison. In certain cases, you might have a drop in accuracy that's not so significant, but if you can have a tiny drop in accuracy and a huge increase in let's say you have not as much discrimination happening in your machine learning model, then it's probably worthwhile to take on that model that is more fair for your application. The last thing you can do is you can fix the predictions. So this is a concept known as reject option classification, or you can correct or override predictions that are sort of close to the boundary and that might introduce some bias themselves. So once again, how can you fix discrimination in ML? It all starts as a process. Make sure you're collecting well-represented data. You're doing your due diligence when it comes to EDA, feature engineering, sort of understanding your domain as much as possible. You're doing a lot of post hoc analysis of your models across several models, always adding in some human review into the process to ensure that you're not introducing any bias or potential bias. And, you know, all of these steps you're seeing on the screen is a sort of an iterative process. You won't get it right the first time or the second time, but it's a process you have to be willing to go through to avoid any type of bias or any type of discrimination that can be introduced into your ML system. And then these are sort of the references that were mentioned across these slides. And of course, these slides will be available to you along with the webinar or after the webinar is over. So now I would like to sort of go over what we offer today in driverless AI, and then sort of a notebook that has been established as well to sort of go over the concepts. So in this notebook, which is linked in the slides, we'll sort of go over this process that I've been talking about making sure you don't have any type of discrimination in your ML application. So, you know, it's a typical Python notebook. We sort of imported our libraries that we need. We're using H2O, and in this case, the data set I'm using is the credit card data set from the UCI website. So you're trying to predict the probability of default next month, and then you're given features like, you know, what's the limit balance, the gender, education, marital status, age. So these are demographic variables which you would probably not want to use in the model itself. And then, you know, we go about importing the data. We go about, you know, sort of doing some recoding of the data to make sure that all the features make sense. And then we train a classifier to predict the probability of default next month. In this case, it's the H2O GBM classifier. We go about building this model, and then we first look at the variable importance of the model itself, and we can see that the most important variable is page 0, which is your payment status of the most recent month, which makes sense. How your payment status was the month before will probably heavily affect the outcome that will happen next month. And we also looked at contributions from Shapley, which is another type of variable importance that's a little more robust than a typical GBM or random forest variable importance. And we can see that page 0 comes up on the top as well. Now, as we're going through this process, we'll set up another data frame that we can use with the predictions attached along with the actual, and then we'll first figure out the probability cutoff that will maximize the F1 score, and we'll try to see, you know, what cutoff is needed to predict that they will default or not default. So in this case, the one we found is 0.21. So this is the cutoff we'll be using for the rest of the analysis. So the first thing we'll do is we'll just look at some raw confusion matrices, which is sort of goes into disparate impact. A lot of disparate impact analysis has to do with looking at confusion matrices and getting data from these matrices and then applying disparate impact. So the first one we look at is the general confusion matrix of the model. So we can see that the true negative and the true positive cells contain the largest values. So it's a pretty accurate model that we've made here. The first thing we'll look at is we'll look at the confusion matrices by education level, which is one of the features that was used. So the education levels here are, you know, they've completed college, high school, graduate school, or another type of education level. And then we can break this down by each level and build a confusion matrix per level. One thing to notice here is that the other level does not have much data in it, which would indicate to you that, you know, maybe we're not capturing as much information as we want about this particular group. While the other levels like high school, university, and graduate school, they seem to have a lot more data around them, which is probably a good representation. Another thing we can break down is the gender variable. So we can look at the confusion matrix for male and for female. And then we can see from here, it's a pretty well represented sample. I don't think we have to worry about any issues in terms of the data at this point. So now we're going to start getting into disparate impact analysis. So disparate impact analysis is a post hoc step, and what we're trying to see is certain metrics across different groups. So in this case, I've made a list of metrics over here that we'll be looking at. So for example, adverse impact, and then here I've tried to describe what that means. So adverse impact is how often the model predicted default in this case for each group. We'll look at accuracy, so how often the model predicts default and non-default correctly per group. Look at true positive rate, precision, so specificity, negative predictive value, etc. Like we can look at all of these metrics per group if we use disparate impact analysis. So these are just some utility functions that we will use. So the first one we'll look at is we'll look at disparate impact analysis across each education level, and we'll compare it across all these metrics that were mentioned before. We can, and I should mention that the cutoff we're using is 0.8 and 1.25. So anything that falls below or above these cutoff rates, it can be flagged as sort of a potential disparate impact occurring. This is just sort of the standard that's used. It's called the 4/5 rule. So we'll use that in this analysis as well. So based off looking at this, we can see that there might be some adverse impact happening, or not, yes, adverse impact and other types of disparate impact happening for the education other. This is because it's, it's the smallest group, so it's not too surprising that the GBM is struggling to capture this type of information. We can continue this process by looking at gender as well, and based off of that, we can see there might be some disparities happening, especially for false omission rate. And so the false omission rate, like is mentioned up here, it says out of the people in the group the model predicted would not default, how many the model predicted incorrectly would not default. So that's what we can look at here, and we can see there is some disparity between male and female. We can also look at the false negative rate for education as well. So like I mentioned before, these are the parity thresholds we'll use, and then we'll continue doing the same analysis, but now we'll look at if any of these are flagged as having disparate impact. So we can see if we compare males to females, means false omission rate seems to fall below the threshold we're interested in, and the rest seem to be okay. So like we saw here before, we're seeing some maybe potential disparity, but we haven't looked at it closely enough. This is just the chart we're looking at. So we can dig a little more deeper and compare it, and we can see that it is indeed below the 0.8 threshold that we have set for ourselves. With education as well, if we're comparing everyone to, let's say, graduate school, we can see that, university might have, comparing university to graduate school, there is some disparity happening here. We can see some happening for other when compared to graduate school, when the graduate school level as well. And once again, this could be because we have a small sample set for the other class. So once again, we're looking at false omission rate, and I've sort of highlighted where the region is that we want to be within. And you can see that for this case, it falls below the 0.8 threshold that we've established for ourselves. And then for education, looking at false negative rate, you can see that high school is falling below some of these other categories, and other is falling above almost every category. So this is a way to sort of look at disparate impact from a notebook and charting standpoint. The next thing we'll look at is sort of if there's parity going on between all the levels that we're interested in looking at. So in the first case, we'll look at males and females. And we just want to see that the different metrics we're looking at are actually within bounds of what we set. So in that case, we set it to be 0.8 and 1.25. So a lot of these are showing up as true, meaning they fall within the bounds we have set for ourselves. You can see over here that type 2 parity seems to be false between males and females, and up here type 2 parity is fairness in both false emission rate parity and false negative rate parity. So it seems that we're not establishing those parities that we want to see. So we're able to identify that using this post hoc analysis. And then, of course, we can apply the same to education as well. The main thing that this notebook will introduce is sort of the fair lending measure that I mentioned before. So we have this concept of marginal effect. So that's the percentage difference between a reference and a protected group. And so this is the reference percent minus the protected percent. And then we sort of go about making this function here, and then we calculate it, and then particularly we'll look at males versus females, and then we can see about 68% of men are awarded a loan by this model, and about 72.8% of women are awarded a loan. This results in a marginal effect of negative 4.7. So since it's negative, this would indicate that a higher percentage of individuals in the protected group were awarded a loan than in the reference group. So we are not seeing any form of discrimination in this case when it comes to the reference group versus the protected group. Also, the magnitude is not as large, so that's also a good indication that we're not seeing any type of discrimination as well. The next metric we can look at is the standardized mean difference, and this is also known as Cohen's d. So this is the mean value of the prediction for the protected group minus the mean prediction for the reference group, all divided by the standard deviation of the prediction. So like adverse impact ratio, this also has some type of threshold, which is usually 0.2, 0.5, and 0.8 for small, medium, and large differences, respectively. So, we're looking at these measures here to figure out how big of a difference we're seeing. So we can go about calculating that for gender again. And we can see the male mean is about 0.23, the female is about 0.21, and then the standard deviation of the outcome is 0.9, and the standard mean difference is negative 0.10. So in this test set that we're looking at, men receive a higher average probability of default than do women. This difference is evident even after we standardize with the standard deviation of the predictions, but the difference is quite small. It's below 0.2 between men and women. So this would be a very low disparity that we're looking at here. Now, we can also look at this individual disparity. So this goes into looking at sort of the potential local bias that we're seeing here. So we can start breaking this down by looking at sort of the top 3 outliers. And we can see the top 3 outliers here are all, they're all females, but then we can see that their payment statuses are quite bad. So, their most recent payment, they're about 2 months late. The one before that, 2 months late, 7 months late before that. So they have a pretty bad track record in terms of paying their statements on time. So this is the case where we can't really say that they weren't discriminated against by the model, but at least we're able to see a very clear picture as to why the model decided that they do have a high probability of defaulting next month. So this notebook sort of goes over how one can run disparate impact in an ML application, how one can look at sort of local biases. This is not, every local bias you can look at, but just one particular example you can look at. You can also slice and dice your data your own way as well. And this is sort of a way of doing it today from a Python notebook standpoint. Now, in driverless AI, I ran the same experiment, and you're actually able to get this out of the box. by just learning the MLI module itself. Now, this is, once again, in that previous notebook, I was talking about looking at males and females for the most part, so that's sort of a typical example you might see in the literature or in a regulated industry. And with Driverless AI, we're offering this right out of the box after you build your experiment. And instead of doing the manual effort of building a notebook and going through and making sure everything is checked off, we ourselves can provide you this information automatically, and then you can see what is going on with your data. So as you can tell here, a lot of these metrics are the same as that notebook I was showing. Actually, they're all the same. So in this case, you're able to see everything in a much more automated fashion, in a much more intuitive fashion, I think. So for example, here we can set the reference group to female. So all the metrics you see here are comparing females to males, and we can look at adverse impact, accuracy, females versus males, and we can look at the same thing we looked at in the notebook, but no manual effort from our part. With that said, I think I'll conclude the webinar and open the floor for any questions.
Great, thank you, Navdeep. Yes, if you do have any questions, please feel free to start typing them into the questions tab in your console. So we'll wait for a few to trickle in. In the meantime, while we're waiting for questions to come in, just want to remind everybody that this presentation is being recorded, and we will provide the slide deck through the same link that you used to register for the webinar itself once the session has concluded. Okay, so first question I'm seeing here is, how do you see companies using this approach to document the non-discriminatory nature of their AI ML implementations?
So the question once again was, how do you see companies using this approach to document the non-discriminatory nature of their AI ML implementation? I think this approach, if you're referring to sort of this responsible ML approach, it has to do with sort of avoiding bias and making sure you're building fair applications, but at the same time it also has to do with increasing your understanding of what you're trying to achieve in your ML system. So using this approach, you could, let's say, maybe not have any bias or any discriminatory actions happening in your ML system from the get-go, but at the same time, by using this approach, you will increase your understanding, I think, of what you're trying to achieve. You'll have a lot more documentation on what you've done, and sort of that is just I think a hallmark of good data science is to ensure that every step of the way is covered and every step of the way is understood at the highest level.
Great, thank you. And then the next question I'm seeing asks, where does the 4/5 rule come from? Do you have any references you could share?
Yeah, so the 4/5 rule sort of comes from sort of an industry standard. I think it comes from more banking. The reference should be in this talk, but if it's not in the talk, I will be more than glad to add it before I hand this off to Patrick to upload to the webinar site.
Great. And this is an interesting question. What can companies do to maintain transparency, and even more so, what if you're also a company that isn't in a regulated industry? What can you do to prepare yourself for this type of action?
Yeah, so I think to maintain transparency as a company, I think what you have to do is sort of maintain transparency within your own organization. So by that I mean, if you're building an ML system, if you yourself can understand a lot of the decisions it is making, and you can justify a lot of the decisions, if not all the decisions, probably the latter is more hard to get to. But if you can sort of reach this transparency yourself before you deploy an ML system or any type of application, then I think you're in good shape when it comes to presenting it to the population at hand. And of course, this type of transparency can be achieved through sort of this flow diagram that I've shown here, sort of this process that we've sort of come up with at H2O, and we think is sort of the right way to do things. So I think by doing that, you can reach a great level of transparency. Sorry, what was the other question?
Oh, and you know, if you're not in a regulated industry, what can you do to be at least aware of this, or you know, just educated?
Yeah. I think if you're in a regulated industry, you're probably already doing most of the stuff I've spoken about. So regulated as in like banking, insurance, those type of things. But if you're not in a regulated industry, you should still try to practice a lot of these things, if not all, because they will once again just increase your understanding of your ML system. And then if you can increase that type of understanding, and you can go about debugging issues that you might encounter in a more efficient manner, then I think you're in good shape to avoid any detrimental actions that might happen to you in the future, whether it be from a consumer or whether it would just be, you know, hindering your business itself because your model's not performing up to the level it should be.
Mm-hmm. Great. And if you do have any additional questions, please feel free to keep those coming. Okay, I'm not seeing any additional questions come in, but definitely want to thank Navdeep for doing a great presentation and taking the time today. I would also like to thank everyone who joined us for the live presentation. The presentation slides and the recording will be made available on our Bright Talk channel, and we wish you a great rest of your day.